Before we jump into thermokinetic energy, let's take a minute on energy in general. We can divide energy into two main categories, potential and kinetic. Potential energy is energy that is stored and ready to be used. This could be a spring, a battery, a tank of gas, and the food we eat. When we use this energy, it is transformed from potential to kinetic energy. The word kinetic describes anything relating to or resulting from motion, and the different forms of kinetic energy are the result of various movements. Light is the movement of photons, or tiny packets of energy emitted when electrons move from a higher energy level to a lower energy level. Sound is the result of the movement of waves of air. These sound waves move our eardrums, and our brains interpret this as sound. Thermal kinetic energy, or heat, is the result of movement on the molecular level. Molecules with more kinetic energy are moving faster and are hotter than slower moving molecules with less kinetic energy. Let's take a look at this model to help us understand. The moving spheres represent individual molecules of water. Imagine the material on the left is the hot liquid water, and on the right is solid water, or ice. On both sides, the water molecules are moving, so they all have at least some kinetic energy. The faster moving molecules are darker red and have higher kinetic energy. The molecules on the right are moving too, just a lot slower. Their kinetic energy is low enough that they can't break the bonds between themselves and their neighbor. They are barely moving at all and are stuck in place, which is what it means to be a solid. The faster moving liquid water molecules can flow past each other as we would expect a liquid to do. When we remove the barrier, the faster moving molecules in the hot water bump into the colder, slower moving molecules of water and transfer their thermokinetic energy. Whenever these molecules collide, the faster, hotter molecule will always slow down, and the cooler, slower molecule will speed up. This means that heat and any energy transfer is always from high to low, never the reverse. As the molecules transfer energy, instead of having a group of mostly dark red molecules and a group of mostly white molecules, the color and the kinetic energy has been spread evenly among the molecules. From an energy perspective, we can't tell which started as ice and which was hot water. This is also what we would expect if we were to pour hot water into a glass of ice. Eventually, the ice would melt, and we would only see liquid water. So, we saw what thermal kinetic energy looks like on the molecular level with the model. And now, let's take a look at it through the infrared camera. Before we do, though, take a look at these pitchers of water. You can see they are both clear. They look about the same when you're just using your eyes. Through the infrared camera, though, it's clear that they are different colors. The hot water is a different color from the cold water. Let's see what happens when we pour them together. And I want you to think about, what do you expect that middle temperature or the middle color in the middle bucket to be after I pour these pitchers together? So we can still see the remaining temperature in these pitchers through the infrared camera. And for reference, we'll put them next to the middle bucket. And as that middle bucket warms up, you can see that the color of the middle bucket is about the middle color between the cold water pitcher and the hot water pitcher. So that thermokinetic energy has mixed and evened out, just like we saw in the model.
So today we're going to use liquid nitrogen, and we're going to use a balloon, and we're going to see what happens to the balloon when we blow it up. When using liquid nitrogen, it comes in a container like this. You definitely want to use a glove. We're going to take this off. I'm going to grab the top, because if it splashes on your hand, you could get burns. And we're going to put quite a bit in the container. It's very, very, very cold. It is a liquid, and as you can see, as it turns into a gas, it comes out and rolls over the side. And as you all see here, we're going to use a regular standard balloon. As I blow this up, we're all going to know that my air blowing out is going to be like 98.6. So basically, we're blowing hot air into the balloon, and we're going to take hot air balloon and put it into a cold environment. So now the prediction we always ask everybody to figure out is, when we put this balloon into this cold environment, is it going to shrink? Is it going to explode? What's going to happen? Let's see. What's happening? Haven't heard a boom yet. It hasn't exploded. We're still pushing down into it. The balloon continues to go into the liquid. Looks like to me the balloon is actually getting smaller to the point that it's flat. So the molecules, these warm molecules, now get in there, and they're they've gotten just closer. And now what's happening is their heat is heating back up, because the room is what, 74, 75? So hot that now it's actually stuck on the pliers. As you can see, it rolls around. You can see the cold spot still on it. It's still expanding. It's becoming back to its same shape. So if you made a prediction that it wouldn't explode, it would just get thin and small. That's what's happened there.